So I'm going to approach this problem from a purely geometric perspective, and the language that I speak is Cartan-style exterior differential systems and G-structures and equivalence problems. So we want to convert this problem to a problem in geometry. So here's the ambient geometry that we want to think about. So jet space is, so I'm considering functions of n independent variables and one dependent variable. Jet space, at least locally, those of you who are in the know that this is a lot more complicated as a bundle. But anyway, locally anyway, we have independent variables, a single dependent variable, variables representing the first derivatives of the dependent variable, and variables representing the second derivative. So the top part of jet space is sim2Rn, where Hessian matrices can live. You should think of this as a bundle over the bottom space Rn. So any function u from Rn to R gives us a jet graph, right? Simply the graph of at every point you get the function, its gradient, and its Hessian. And the important thing about jet graphs is that they're integrals of the contact system. So the contact system is simply identifying that you want pi to always represent the derivative of y with respect to xi, and you want uij to always represent the second derivative. And a contact transformation is, at least for today's talk, a diffeomorphism from the manifold J2 to itself that preserves the contact system as an exterior differential system. The important thing about contact transformations is that because of the way this ideal works and how it preserves the notion of derivatives, it takes jet graphs of functions to jet graphs of functions. If you want to be technical, it takes holonomic sections to holonomic sections. But for the moment, let's just think about jet graphs of functions. That's the ambient space that we work in. So to me, and I think to most geometers, a nice way to think about a second order PDE is as a hypersurface in jet space. So think of a function from jet space to R and just look at its inverse image, and at least locally, generically, using the implicit function theorem, that gives us a hypersurface. So for the wave equation, you could write your function in the top variables this way or this way, depending on which signature you prefer. And another famous equation is this. This is a version of the first flow of the dispersionless Kp equation. And these are all certainly just functions, and you think of their inverse image at 0. So that's, to me, what a PDE is. So again, contact transformations take jet graphs of functions to jet graphs of functions. Of course, they're diffeomorphisms. They're also taking hypersurfaces to hypersurfaces. So in particular, they're taking solutions of PDEs to solutions of PDEs, right? A solution to a PDE is a jet graph of a function that lands in f inverse of 0. So anything we want to do about the geometry of PDEs better be up to contact transformation. It preserves kind of all the important facts about a PDE that we ought to care about. And we want things to be coordinate independent. And that and more is what the contact pseudogroup gives us. The problem is that the contact pseudogroup, and you can ask people like Ian who have studied this for many years, is just unbelievably big. I mean, it's just unimaginably huge and really hard to get any sort of grip on. So what I'm going to do today is describe how to simplify the problem, simplify the context, so that the local geometry is actually tractable and makes sense. And the thing that's really neat is that we're going to maintain the original idea of understanding contact classes of PDEs, while at the same time making a geometry which fits beautifully into the program of this week's talks. So let me do that. So I'm going to consider only what I personally call Hessian PDEs. I think I'm the only person who've called them this in the literature, but it's a reasonable name. They've also been called, in the hyperbolic case, dispersionless Hirota-type equations in 3 variables. So, but I'm just considering functions of the form sim2Rn to R, right? So they only depend on the second derivative part of the function, its derivatives. So why would I consider this class? First of all, many of our favorite PDEs are in this class, and we've spent many hours in the last few days learning about the Laplacian in various ways, right? Certainly the wave equation and the other form of the wave equation and the other example I gave are in this class. And secondly, we can understand contact transformations on this class very nicely. So if you consider the contact transformations that preserve this class of PDEs, it's very easy to understand. There's a natural action of the conformal symplectic group on symmetric matrices. In fact, you should think of symmetric matrices as the Lagrangian Grassmannian and n2n for some symplectic form. So it's easy to understand the group action there. And third, thanks to a lemma of Dennis from a paper he wrote last fall, if we can understand the conformal symplectic classification of Hessian PDEs, this gives us a coarse version of the contact classification of all second order PDEs in the non-degenerate case. So we want things that are genuinely second order. But they aren't first order PDEs we somehow shoved in second order jet space. We want them to be honestly second order. But if they are, then understanding the conformal symplectic action on Hessian PDEs gives us a way to access some information about the full contact classification of all second order PDEs. Okay, I'll mention Dennis's paper once more a little bit later. It's a great paper. So let me describe the intrinsic geometry, which is the topic of this talk. Now, I'm very pedestrian when it comes to geometry, right? I like G structures and connections and symmetries, and that's about it. And I'm hoping to learn more about the BGG complex and all these great things. But for the moment, I'm just thinking in terms of G structures, because that's all that I really think I understand. So I'm going to write down a G structure on a hypersurface in Sim2Rn. So let's have it abstractly be called M. And it's identified as a hypersurface through some map I. And of course, df can be written, if the duij's are the flat framing on Sim2Rn, then of course there's some coefficients here which describe df. And this is nothing but the leading symbol of the PDE in these coordinates, that phi. So we like G structures. There's a natural symmetric action of GLN on Sim2Rn, or at least on its tangent space. And so I'm going to do a frame adaptation to, I'm going to fix phi, but allow the framing to change. So now I've changed kind of the U-dependent, the pointwise dependence from the leading symbol to the framing in which I'm writing the leading symbol. And of course, the fact that you can do this just follows from Sylvester's law of inertia, right? You just do G transpose AG to put G in terms of its eigenvalues. So now the infinitesimal picture is this. We have the tangent space of the manifold Sim2Rn, and it has a framing to the vector space Sim2Rn. df is, of course, the one form whose kernel is the image of TPM. And TPM, through this co-framing, is identified as the space sort of orthogonal to the df direction, right? It's the kernel of df. So S is this vector space, and Sim2Rn, the vector space, is this vector space plus R. In particular, S is the space of symmetric phi traceless matrices, which, if you conjugate it, if you kind of shift the coordinates a little bit, it's something you should recognize as the space of traceless Ricci tensors for the inner product phi. So the space of Ricci tensors, of traceless Ricci tensors, is in some sense it's exactly where the frame of M takes values. Okay, so I'm using that vector space, the traceless Ricci tensors, as the co-frame destination. Yes.
You're not actually calculating the Ricci tensor of it.
No. I'm just saying it's the vector space which could be, right? Its definition is exactly this: symmetric phi traceless matrices sitting inside this vector space. Okay, but as an abstract vector space, it's perfectly well behaved. Right? I mean, well, it's a vector space. Okay, wrong clicker. Okay, so let me kind of say this in greater detail in terms of defining a G structure. Contact transformations act on TP Sim2Rn, which is of course a space of symmetric matrices. And the action you see at first order is simply the symmetric action of GLN. So that's kind of the natural action that's happening here on the ambient space. And if you restrict that action to find the stabilizer of S, the subspace, it gives you a group G sitting in GLN, which is defined by this relationship. It has to preserve the phi direction, or it has to preserve the fact that we're phi traceless. That group, if you stare at, of course, that's the orthogonal group for the metric phi. Or in other words, if we're thinking of hyperbolic signature, this is the Lorentz group, the total Lorentz group. And we're allowing, I say C there, and we're allowing scalings, right? We don't care about changing df by a constant, of course. So now what I've just done is define a G structure on M, which is now just intrinsically defined on M. You can throw away all the stuff on the right-hand side, and you have M with a frame taking values in a vector space and a group acting on it naturally. So that's the G structure that we're going to study. Okay, so this picture maybe, if you don't like pushing around coframes and taking tautological forms and so forth, this maybe isn't so satisfying, so let me give you a different description of this. Consider the Veronese cone. This is an object I know is popular among many of you. So the Veronese cone is a space of, within Sim2Rn, the vector space, it's the cone of rank 1 symmetric matrices. So it's things that look like V transpose V, where V is a row vector. Row vector, right? So, okay, you can projectivize, and this is the Veronese variety sitting in the projectivized Sim2Rn. And of course, the Veronese variety is isomorphic as a variety to just Rn. And so, it's not too hard to see the symmetry group is just GLN or PGLN, depending if you want to projectivize. So there's one of these sitting in each tangent space of the manifold Sim2Rn. Right? So you have Sim2Rn as a manifold, in each tangent space you've got a Veronese cone. Now I'm taking a hypersurface of the manifold Sim2Rn, and so the tangent space of that hypersurface, right? This is the kernel of df right here. Intersects that Veronese cone and gives me a subcone of the Veronese cone. So the symmetry group of that subcone C is exactly this G I described before. So if you want, you can think about a manifold M with a distribution of these cones, which happen to be hyperplane sections of the Veronese cone. What? OK, thank you. That's the signal? OK, great. Perfect. Good timing. OK. So this is a non-degenerate Hessian PDE. A non-degenerate Hessian PDE is a distribution of cones, and this is equivalent to saying you have a G structure. So the obvious task is to classify either the distributions of cones or the G structures. And in my world, this means using the method of equivalence, although I think Igor would prefer using what he was describing in his talk a little bit earlier. But either way, you're going to get to the same answer. And actually, this isn't just a geometric game. This is very closely tied to the analysis. So in a couple of papers between, well, I guess even going back to about 2005, Ferapontov and his group and his various collaborators have this notion of hydrodynamic integrability of a scalar PDE. So this is basically saying that you want your PDE to be packed with conservation laws in the sense of semi-Hamiltonian or rich systems. So if you know that analysis, we want lots of those. We want this to be consistent with semi-Hamiltonian systems. If you don't know what that means, just we want lots of conservation laws, and it's a very strong symmetry condition. And they demonstrated that this notion of integrability for the PDEF corresponds to this manifold M with its distribution of cones having many foliations by subspaces that intersect that cone maximally. OK, so here's so this is the picture, right? We want to study these G structures, and if we can, impose these integrability criteria. I don't know if I'll get to the integrability criteria in the 3 minutes remaining. So here's the first theorem we can encounter. And again, this could be maybe achieved in some sense in a more simple way than what I did by using what Igor mentioned, or maybe some of the chasing of hieroglyphics that Mike has been talking about. But I'm not familiar with that, so I used what I know, which is just using the equivalence method of Cartan. And the neat thing, although it's maybe not so surprising, is that the G structures over these abstract Hessian PDEs intrinsically have closed structure equations. And the structure equations are things which are now familiar this week. The totally traceless, the torsion takes values in a totally traceless symmetric matrices, or the totally traceless symmetric tensor of the coframe space. And there's a curvature in a wedge space, a traceless symmetric space, and a couple more representations that you have to throw in there to make it complete. And so for any given number of independent variables, we can actually give a local classification, I guess a germ-wise classification of these structures by simply picking these values at a point. So in some very clear sense, okay, there's only a 39-dimensional space of second-order PDEs in 3 variables. I know that's an absurd statement, right? But what I'm saying is that if you look at the intrinsic structure on the PDE when it's second order only, all you have to do is specify these numbers. And because in the hyperbolic case, this is the Lie algebra involved is SO21, that's SL2, and so we just use SL2 representation theory to find these where we have to take the different values. A very similar thing happens, of course, in 3+1 variables, which is the case I really care about, obviously, because that's where we live, at least apparently. And so you can again just know exactly what the irreducible representations are. And incidentally, I'll finish here and just skip the integrability part. Two variables is very interesting. And if Dennis had given a talk, it would have, I think it might have been about this. So Dennis studied this in a both in his thesis and in a paper released last fall. He looked at second order hyperbolic PDEs in two variables. And of course, from my perspective, from the perspective of this talk, there's no geometry there because there's no conformal geometry on a plane, on a two-dimensional surface, right? Everything is conformally flat. So there's no intrinsic geometry, but there is extrinsic geometry, how you decide to embed that into Sim2R2, and that's what Dennis studied in great detail. So I'm kind of working on the intrinsic part in higher dimensions, and he completely gave a very satisfactory answer to the extrinsic problem in two variables. So I'll skip integrability and finish there. Thank you.
Questions?
Mm-hmm.
If I gave you a single second order PDE, three variables, could you tell me, and it's just some messy thing, can you tell me when it's expressible only in terms of the two jets? So do you have a...
No. Well, I can't.
How you get into this class?
Right. So the way you get the way to think about this is that you take a second order PDE with any terms at all. It can be extremely nonlinear. It doesn't matter. But you so that's just some hypersurface in jet space. But jet space is a bundle, and you know that as a second order PDE, this hypersurface has to be transverse to the fibers of that bundle. So you just pick a fiber and intersect it, and that's what I'm looking at. So you should really think about this as in the bundle J2 over J1, looking at the intersections of any PDE with the fibers. So that's what Dennis pointed out to me last year. Yeah.